Homophily, a single English word that defines birds of a feather flock together. Let's look at some flocking simulation today. So you know about flocking, right?
The birds of a feather?
Yeah, birds of a feather flock together.
Yeah. Okay.
So this video specifically covers flocking of birds. All right. And instead of me just explaining over words, let's look at a video and I'll show you what I mean by that.
Okay.
So I have a video loaded here and you can see there is a set of birds. So I'm just going to play this video.
Okay.
I'll leave a link to this description, a link to this video in the description. And let me just forward through this, I think, over here. All right. So when scientists first observed this kind of behavior, there was an assumption that there is a leader among these birds that's guiding all of these birds into a pattern or into sort of these sort of beautiful undulating patterns.
Right.
All right. But then some other smarter scientists came to the realization that that's not what is happening. Each individual bird in this flock is essentially guiding its own plot through this flock.
Wow.
Now, the evolutionary reason why birds flock or animals flock is because it gives them advantage in numbers. Yeah, strength in numbers. This same sort of pattern emerged in fishes also. Species that have been separated by millions of years of evolution do the same thing. And this is to make themselves seem bigger in the form of a prey and not to give like a single target for the predator to come and attack.
Got it.
Alright, so that's the evolutionary reason why it happens. But the mechanism of flocking itself has been a subject of study in many interesting papers and all of those things.
Okay.
All of these things say that the flocking essentially happens just due to three forces. Number one is that the birds have to travel in the same direction as its neighboring birds. Birds have to go closer to each other or go in the same direction as the other birds, and they also have to ensure that they don't collide with any other bird.
Right,
so let's just look at this small little presentation that I have prepared. Right? So flocking is striking a balance between these three forces. The forces are alignment, cohesion and separation. That's all. There can be other forces also, but the major forces that are in play are alignment, cohesion and separation.
Wow.
So alignment is when in range of other birds, the boids will try to align itself with other boids. They do this by finding the average speed of the other boids and normalize these averages. I'm calling it so birds are the actual physical biological things, because we are simulating them in JavaScript or in a computer program, we're calling them boids.
Boids.
Yeah. I mean, I think it's derived from both bots and birds. It's like a bot plus a bird becomes a boid.
Right.
So anyways, that being said, that's what alignment is. All right. So basically match the speed with your neighboring birds.
Got it.
All right. Second is cohesion. When in range of other boids, the boid will try to move to the center of mass of other boids. This is done by finding the average of their positions and not their speed and changing the boid speed to align with the average position. All right. And then you have separation. All right. Get close to your neighbor, but not too close that you go and collide with them. So that is what separation is. All right. This is the opposite of cohesion. And it works in exactly the opposite way. If you are within, let's say, a specific distance of another bird, you, by finding the average of positions and changing the boid speed to move away from the average position.
Yeah, makes sense.
All right. So with that being said, let's code this up.
So didn't we study in school and all that they make these patterns to avoid wind friction and all?
I think it's got something to do with predators.
That V formation and stuff.
Yeah, so that is V formation. That is not flocking. So geese or I think ducks also. Ducks that migrate, ducks or geese that migrate, they do in that V formation.
Just for that is not flocking.
That is not flocking. So that is if you have even cyclists, for example. If you have a cyclist in front of you, air resistance is lower for you, so it's easier for it to cycle. It's the same concept. So these birds, they follow in a V formation. in basically the wake of the bird that.
Right. So
Here's the most important part. They every now and then they'll switch positions because the bird that is leading will get tired, so he'll take the position behind.
Right.
And so on and so forth.
So then that has a purpose, right?
Yes.
To reduce wind friction.
Yeah.
Then what is the is there a purpose to flocking in
Predator
biological?
avoidance.
That's what you said.
Yeah.
Predator.
So for an eagle,
Right.
it is very difficult for an eagle to attack a single bird. Yeah, I think the
Or very
concept
easy to attack a single bird.
Yeah. Yes. A bird that is
separate.
not part of a flock will be easily visible,
Ah.
and you can pinpoint it out and you can grab it.
Ah.
It's more apparent in fishes, I think, which is why.
Right.
Yeah.
Which is there in that movie and all also. Right.
Yes.
Sure.
So with that being
Makes
said,
sense.
let's code it up.
Uh-huh.
Let's see what it looks like.
Got it?
All right. Let's look at how I have set this up. As per usual, I have an index.html page where I include two files, a Boid JavaScript file and a flocking JavaScript file. The Boid JavaScript file will host the Boid class and the flocking would perform the actual animation. I have a canvas on the screen of size 1600 by 800. Let's look at the Boid class. For now, it's just a skeleton class, which has a constructor, an update function, and a render function. The render function is supposed to render the Boid onto a canvas. I'm calling it canvas over here. It should in fact be a context. So we'll change that at a later point. I have a flocking JavaScript file, which has the width, height, and context predefined. These are all initialized in the init method, which also ultimately calls the flocking function, which is simply a loop function, and the loop is achieved using a request animation frame. All right, with that being defined, let's fill up the Boid class. Before we begin, let's define some common variables to store the minimum and maximum velocities, an array to hold the boids, and the boid size. The constructor of the Boid class takes an initial value of x, y, and speeds in the x and y direction. We'll also initialize all the boids with their own color. We'll define a function here called addSpeed, which will add a speed parameter to the boid's speed. We'll also check the minimum and maximum speeds allowed when setting the speed values, which is what we are doing right here. Once we do the x, we'll also define the y as well. Next, the update method will add the speed to the x and the y components of the boid. When adding the speed, we'll check for the boid's bounds in such a way that if the boid flies off the screen, then we'll simply have it appear from the other end. All right, so here is us coding those in. The render method is pretty straightforward. We want to give the boids its triangular shape. That shape is actually defined at the top right hand corner of the screen. To do that, we'll just simply calculate the angle behind the boid's position at a 0.3 degree radian, which is what the get angle does. So we use the get angle and then we define 2 points behind the boid that are 0.3 radians away from that point. So once we define those 2 points, all we have to do is draw a line and join all of them by using the close path. In the main file, we'll initialize how many boids we want to animate on the screen. In this case, I have used 300 boids. The boids are initialized at random locations on the screen. They're also given random speeds of value between -1 and 1. Once I've done that, I'll also initialize the random color that has to be provided for these boids. Next, we'll initialize the boid itself and we'll add it to the big array of the boids. In the render function, we'll first make the canvas black in color, and then this function simply calls the update and the render of all the boids. All right, let's see that on the screen. This is what the boids look like. So right now there is no flocking behavior because we've not defined it yet, but you can see that the boids look exactly the way we designed them. They are also exactly the same color as we defined them. All right. With that being done, let's go ahead and define the boid flocking behavior. We'll declare a variable here that defines the alignment radius. This is the imaginary radius that each boid considers to look for other boids to align with. The alignment function itself is pretty simple. All we have to do is find the average speed of all the boids in the alignment radius and calculate their total speeds. Then we simply average out the speed and normalize it. So here is us getting all of the boids within a specific alignment radius, calculating their total speeds. Now, if there are neighbors within that alignment radius, then we simply calculate the average. The average is then normalized. Normalization simply means to turn the final value to a value between 0 and 1. So once I have that value between 0 and 1, I just set the alignment speed and return that point back. All I have to do now is call this function in animation and set it to the boid using the add speed method. Now that alignment is complete, let's look at what that looks like. So you'll see that they start off at random directions, but then pretty soon they get aligned with each other and they sort of move uniformly in this one direction. All right, but that's just one force. We still have cohesion and separation to do. Let's add those two forces and let's see what that looks like. Just like alignment, we will also have a cohesion distance. This value is usually greater than the alignment distance. We'll declare a do cohesion function that simply calculates the average position of all the boids in the cohesion distance. To do that, we'll first have all of the total values calculated. So we'll have to calculate the total first. We'll loop through all the boids, but we'll only consider those boids that are within that cohesion distance. So once we do that, once we calculate the total, like so, we'll simply calculate the average. The average, of course, is just the total divided by the number of neighbors that it has. And from the average, we'll calculate the normal. Now this division by 100 that I'm going to do is simply to make sure that the normal values remain between 0.1 and 1, or basically values between 0 and 1. So once we do that, we'll just simply return the speed and we'll give cohesion the same treatment that we gave alignment. Let's look at what adding the cohesion code has done to the boids. So when I refresh the screen, you can see that the cohesion works very well as the alignment. They all do actually flock with each other, but there is the final piece of this puzzle that's missing. That's the separation. They all amalgamate into this one mass, but we don't want that to happen. We want these boids not to collide with each other, but to maintain separation between them. So let's code that in now. The separation radius is usually a very small value compared to alignment or cohesion radii. However, the do separation function is treated in the exact opposite of cohesion. Thus, instead of adding other boid positions, we will subtract the other boid positions. This will give us smaller values compared to cohesion, but that's fine. We don't want these boids to be too separate from each other. Now, once that is done, we will give separation the same treatment as alignment and cohesion. All right, so now that we have programmed the separation also, let's look at what the results look like. When I refresh the screen, you can see that the alignment happens. You can also see the cohesion play out, and now the boids are actually separated from each other. Looks beautiful, doesn't it? All right, I'm going to make a few modifications so that all of the boids don't create it at the same time. I'm also going to give them different colors, but I don't think it's important to show it in this episode itself. And with that being said, let's look at the final results with Ravi. You ready to look at the results, Ravi? Okay. I'll hit the refresh button. And yeah, so what I'm doing over here is I'm generating these boids at random places, and I'm generating them all of the same color so that you can see birds of different flocks flocking together. But when they come in conjunction with other flocks, you can see the flocking behavior happen. Those three forces, the the cohesion, alignment, and separation taking place over and over again.
Right.
All right. So obviously there are other. Yeah. Look at this. These two. Yeah. I mean, if you separate a single one of them out, you can see that they will seek other boids to be, a part.
That group join the bigger group.
Yes. So things like that happen. So I'll refresh it once more just for posterity, so that we get a different random set of boids generated.
Right.
All right.
Wow.
Right?
Yeah.
So obviously there are many things that we could improve upon this. For example, we could give sliders that could adjust the various forces that are so we can make probably the separation much more better.
Yes.
So that they are like even more farther apart from each other and things like that.
That will be a cool idea, right?
Yes. And of course all of this is available on GitHub.
Of course.
Users can or viewers can download this and see it for themselves.
Makes sense.
All right. Makes sense. All right. Let me just switch cameras here. One. So what are we going to do for the next few weeks? I mean, so that's something that I wanted to discuss.
Okay.
Obviously, that ants thing, that the ant colony system is still under works,
right?
But because my laptop is now officially kaput, I'm not able to continue work on that one.
Right.
But a kaput laptop has its own uses. Remember last week we were talking about making a smart mirror?
Right.
We should definitely make that an episode. Right. So the smart mirror project requires a monitor, and then you put it behind a one-way mirror, and then you attach it to a Raspberry Pi, and you can write your own calendar or whatever notifications you want on that monitor. So now we have a broken monitor. We could probably make use of that, and so I'm not saying that we'll do it in the next episode itself, but that's something that we can slot in for one of our for one of our episodes. But next week, thankfully, I thank you for the laptop that you've given me. I am able to set up everything that I need on this one, and then I'm able to continue with ants. All right. So fingers crossed. I hope I find time to finish up the ant colony systems.
Right.
That was it for this episode. Thank you so much for joining. Do like, share, and subscribe this video, and share it among your friends if you or your friends are inclined to development and visual things like the flocking thing that we just saw. This is the channel for you. Come join us on this journey. Thank you so much. Bye.
Ciao.